The Max Planck Society has been involved in trying to detect gravitational waves for a very long time, for more than 20 years, since before I came here. And this institute is somewhat unique because we have here under a single roof experts who are involved in all the different aspects. That means designing and building the hardware for LIGO, constructing and operating the data analysis systems, designing the algorithms, and also predicting the sorts of signals that we would see. And most of the institutions involved in the LIGO scientific collaboration have expertise in one of these areas, but very few bring together experts in all of these different areas. And that was very important here because when this signal first happened, we were very lucky that one of the people who saw this signal could just walk down the hall and talk to somebody who was an expert on the instrument. Otherwise, we might not have known that this was real. ATLAS is the largest cluster in the LIGO scientific collaboration. It has about 14,000 computer cores. It's one of the larger computer systems in Germany and in Europe. And since we started our data taking run, this system has been completely loaded. It's been busy with work from different data analysis groups. ATLAS is one of the largest computer clusters in Europe. And it's the single largest computing resource in the LIGO scientific collaboration. And we use that to search the data for weak signals. It's been extremely useful since we made this discovery to answer important statistical questions like, was this signal a real thing, or could this have happened by random chance or accident? These data analysis pipelines are very important because they're what's watching the data to tell us if something's there. I sometimes like to say that the instrument doesn't really end at the output where the light from the interferometers recombined. The instrument really continues and includes the computing systems that watch that output to find things. So an important part of the instrument is here in Hanover in the large computer systems in ATLAS. So there's the two gravitational wave detectors in the United States called LIGO. Our institute operates a smaller gravitational wave detector called GEO600 here near Hanover. There's a large French-Italian experiment called Virgo in Cascina, that's near Pisa in Italy. There's a Japanese gravitational wave detector called Kagra that's under construction under a mountain underground in Japan. And there's also a potential future gravitational wave detector that's going to be built in India. You see, real gravitational waves would travel through the Earth just like a knife through butter. Actually, that's not even a good example. They travel through the Earth as if it wasn't there. And so, since gravitational waves can just travel right through the Earth, they would arrive at all of these different instruments, but not at the same time. So the fact that you see it at the different instruments tells you that it's real. It must be at all the instruments, otherwise it's not real. And it doesn't arrive at the same time. And the time delays tell you where it comes from on the sky. So we need multiple instruments for two reasons. One, for confidence, to be sure that what we've seen is real. And second, to know where it came from. These are two black holes, and they're black. They don't emit any electromagnetic energy. No light, no radio, no X-rays. The only way to see these is with gravitational waves. And that, by the way, there's really two motivations for building these instruments. One is as a way of doing astronomy, because they let us see things like two black holes that we wouldn't otherwise be able to see. And the other reason is just to see if Albert Einstein was right. We don't know exactly what the signal is going to look like. We have to look for many different kinds of signals, and so we've developed many automatic tools for doing that. And these tools are what at first revealed the signal. And these tools are very sensitive. They can reveal signals that are very hard to see with your own eyes. But in this case, the signal that was found was so strong that you can actually just see it when you look at the data, if you know where to look.